Hi folks, you are already familiar with the LTSpice UI and toolbox. In last couple of episodes, you have become familiar with the basic active and passive elements. In this episode, we'll construct a CMOS inverter using two monolithic P and N MOSFETs, where the P MOSFET has double the area of the N MOSFET for mobility balancing for majority and minority carriers of the respective MOSFETs. We will apply a pulsed waveform shaped like a square waveform as the input to the constructed inverter. We will apply proper DC biasing voltage and transient analysis to check the functionality and performance of the CMOS inverter. So stay tuned, stay focused. Hey guys, welcome back. Today we'll be exploring the CMOS inverter circuit, and we will be using monolithic MOSFET, that is different from the regular MOSFET. Monolithic means the NMOS and the PMOS will be fabricated on the same silicon wafer. So for that, LTSpice has a model called monolithic MOSFET. We will be using that model, and we will be using a pulsed source at the input, and we'll check the response of the inverter circuit using the transient analysis. So without any delay, let's start. Here is our LTSpice. This is my highlighter tool. I'll be using it for highlighting. So this is the blank canvas of LTSpice. Now let me create a new file by clicking this button, and also from keyboard you can use the Ctrl+N. So here is the blank canvas for drawing the circuit. Here we will have two voltage sources. One is for the DC biasing of the MOSFETs. Another source will be used for the input in the CMOS inverter. That is the pulsed input, and the biasing voltage is DC. We'll be having two different voltage sources. Let me first place the two voltage sources. Let me go and click here the component. And if I go at the last, here is the voltage. So I click here for place, and here at the beginning, at the very left, I click here, and there will be another. So add some difference here. So let me right click and it vanishes. So here this circuit is very simple. We have a PMOS in the upper side and the NMOS in the lower side. So let me go and search for the MOSFET. We go to the components, and here I'll search for the MOSFET. So here you can see the MOSFET NMOS4 is there. Similarly, there will be a PMOS and the PMOSFET. You can see here that this is used for monolithic MOSFETs. So whenever you are making a monolithic circuit like CMOS inverter, you should be using this particular MOSFET. So here, let me place the P MOSFET here, and let me right click to vanish it. Again, I will go to the components here, and here, as similar to the PMOS4, we have the NMOS4. So again, you can see it is used for the monolithic MOSFET. We will be using the NMOS4 model. So let me click place and place it just below the PMOS. So we have a NMOS and we have a PMOS. Now let me right click and vanish the whole thing. Let me move the canvas, and here somewhere I will be placing a load resistor. Let me click it, and here I'll be placing a load resistor. Now let me right click and make it vanish. So the load resistance is here. Zoom out a bit. The circuit is boldly visible. The components are ready. It's not a heavy circuit. We have all the components. Now let me do the interconnections. This will be as the biasing voltage. Let me go here, go up to this point, move rightwards, go up to this point, come downwards and click here. Similarly, I'll click at the negative end. I'll go downwards. I'll take a right turn here, go up to this point, click here, go up to this. So now I'll connect this the ground. So basically in MOSFET, as a symbol wise, there is no difference in the source and the drain because both are mirror of each other. So I'll be connecting according to the circuit, and also this has a substrate connection because that is very much important. So here for the NMOS, I'll connect the substrate point to the ground, and for PMOS, I'll connect the substrate the VDD. So I'll name it later, and these two ends will be connected. Now again, we have a common point that will be the input. Come here, come down to this point and pick this point. So here you can see that we have this common point. Connect this point which is the common point to as a output to the load resistor. I think the interconnections almost done. One point is missing, that is the ground. So let me place the ground here. Let me right click and do the interconnections here. So now the interconnections almost done. Now let me connect the voltage which will be applying at the input of the MOSFETs. Point here, and I connect to the ground. Here, go above and connect. Zoom out a bit. You can see the entire CMOS circuit has been arranged. Let me go click the save button, or from keyboard you can click the Ctrl+S. So it will save the circuit. Now I'll rename and add values. So basically if I click on V1, it will be named as VDD. Now I will set the voltage value. I'll right click here, the DC value, I'll give 5 volts here, and I have to click on the name, and I give as this as the V input. I click OK. So this is 5 volt and this will be a pulse waveform. So let me right click it here and go to advanced. Now here you can see that pulse is there. So let me click it, and according to that I'll set the different parameters. And in the theoretical episode I have already explained about this pulse source, how all the parameters like V1, V2, delay, T rise, T fall, T on, period and number of cycles has been defined. I have explained in detail with infographics. So in case you have not seen those episodes, please go ahead and see this episode from the Spice in VLSI playlist. I'll not go to the fundamentals right now as we are in the application level. Let me click on the pulse voltage, and here I will set the parameters one by one. 0, the initial voltage is 0, the on time voltage is 5, time delay is 0, rise time will be 1 nanosecond, fall time will be again 1 nanosecond, on time will be 20 microsecond, and period will be 40 microsecond. So basically we have the half on time and half off time, and the period is divided in that. So it will take a shape of almost a periodic square wave. So after selecting the pulse, I have given the basic values here. You can see and you can note down in your notebook. Here I have given the basic values. I'll not give the n cycles because I'll be using the transient, so I'll not be using the n cycles here. And now I click OK. So you can see it is a bit juxtaposed over the NMOS. I think it's okay. For the understanding, you know what component is there. Now I will go ahead and click these MOSFETs. I'll right click here. Theoretically, you know that in a CMOS combination, the PMOS has a double the area of a NMOS. So that can be achieved that keeping the length same, gate length will be same, because in a technology generally the gate length is same, only the width is varied. So I'll keep the gate length same and the value will be 20 micro. So I'll be keeping the gate length 20 micro, and here width will be 200 micro. And for NMOS I'll keep the width just half of it. So let me click OK, and the parameters are set for the PMOS. And now I'll click the NMOS, and here I will set the length to be 20 micro and the width to be 100 micro. So you can see that the NMOS has a half area as compared to the PMOS. So this is basically for the mobility balancing. That means electron has a higher mobility and the hole has a lower mobility. You have to balance the both mobilities of both electron and holes. Since this is a semiconductor, we have both type of carriers. So that's why this rule is applied. This is a thumb rule for any CMOS circuit, where the PMOS has the double area as compared to the NMOS. And now I will move to the load resistor. So here I will click and name it as R load, because this is a load on which we will be taking the voltage. So this will be 100 K. That means 100 kilo ohms. I click OK. Let me click the save button to save all the work that we have done so far. And so here one thing remaining, I have to add the transient analysis, and also I'll add pin. Okay, I'll name it as input pin or type input. You can see input is labeled here, and I'll click another pin here. I'll click it as output. Port type, I'll click it as output, and I place it here. So the components are done. Now let me add the analysis. So I'll go to the spice syntax. Here I will type dot tran. I'll click OK, place it here, and then I'll right click, and here the transient analysis comes. Okay, so the stop time will be 80 microsecond. That means we will see the response for the 2 cycles. The next value from where the simulation begins, or we will be starting the data to be saved in the hard disk, that is 0, and maximum time step will be 2 microsecond. So here you can see our transient statement has been constructed where the stop time is 80 microsecond, the start time or data saving beginning time is 0, and the time step is 2 microsecond. Okay, so we are all done with the transient, and I'll click OK. And again, I'll click the save button to save all the work that we have done so far. Now, before going any further, let me do a checking of each and everything. We have our input biasing voltage, that is VDD, which is 5 volt. Okay, and here we have a PMOS, and here we have a NMOS, and these are monolithic MOSFET, so they do have a substrate connection, which is for the PMOS is tied up to the high, and for the NMOS it is tied down to the ground. Next, we have another input which will be used in the input of the CMOS inverter, and here we'll check the output across the load resistance, and which has a value of 100 kilo ohms. Here we are using a pulse command to create a almost square wave, although we have rise and fall values here. So in actual practice it will be a little bit slanting when it is rising. Now I think all of our circuit components are done. We do have the ground, so everything is placed, and we will be doing a transient analysis. And this biasing voltage is a DC voltage. So let me clear everything. Let me click save icon, and then I'll go ahead and click the run button. Here now I will go ahead and click the right hand side circuit. I'll do a bit more zooming. I think it is not zooming. I think it has zoomed. So I think now it is okay to see. Now I will measure the input voltage. So input voltage is nothing but the input waveform which we have given as a pulse source. Here I click, hold, drag and release. So this is a pulse source. I come to this particular window, hit the B from the keyboard. I select the below one, and here I go to the output. And here I go, click, hold, drag and release. So now let me bring my marker pen here. So you can see the input waveform is propagating like this, and the output is exactly inverted by the constructed inverter circuit. So we are very much successful in designing a inverter circuit at the transistor level using 2 monolithic MOSFET, where the PMOS has a double area as compared to its NMOS for the mobility balancing. That means the mobility of the hole and electron will be balanced so that the circuit performance will be optimized. So here we have checked the input pulsed voltage, that is almost a square wave we have done, and the output voltage, and which are conforming to the inverter output. So we have successfully designed a inverter circuit using a CMOS structure, and we have done the spice simulation of it using the LTSpice. Now I'll do check the 2 mandatory things that as an engineer you must check. One, go to view, then spice output log, and here I can see there are no errors. Okay, this is must. You must check, even though everything is coming okay, you must check whether there is any problem here mentioned, because for the industrial grade simulation, right, you should not leave any stone unturned for the output. So here we close it, and then I'll show you another thing. View, go to the spice netlist. Let me turn on the pen marker pen here. So here you can see that our VDD biasing voltage is there and it is input the pulse source, which as a text I have already talked about in the theoretical episodes. We have two monolithic MOSFET which are used for the construction of the inverter, and here you can see PMOS has a double width as compared to the NMOSFET. Okay, we have a output load 100K and these models are included using the .lib command from the model library, and we have a transient analysis here. I think we are done here. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in comments in the comment section down below, and bye for today.